All right, so you all, do you have questions here that you're going to move to this? All right, so what I'm going to do is I'm going to do a little bit of a recap of what I think you all have been over in 1040, and then kind of ease a little bit into the first sort of new section here. Anybody know what to make your questions kind of were? They kind of inspired folks to start to think about these things. Very good. That's one of them. So if you have some function and you've got some point here, it's on that. People wanted to know what's the tangent line of this function. And you probably saw in 1040, I mean, who cares? Well, the reason you care is because this tangent line represents the instantaneous rate of change of the function. And in all sciences, change is an important thing. We worry about climate change. If you're into economics, you certainly want to know how your bank account is changing. You want that change to be positive, not negative. Change is very, very important. So this is a major question, slope tangent line, and this is often called the derivative, right? That you all messed around with in 1040. Right? Does anybody know what the class problem is? You all probably didn't get to this. But another class problem, you have a function. 2 points here, A, 2 points along the x-axis, A and B. Another classic question is, what is the exact value for that area? And you know, I almost think I got this problem licked because I got a straight bottom, 2 straight sides, but I've got this curvy roof top, right? And that's where it gets a little, it's not a triangle, it's not a rectangle. I'm not sure, right? This is another classic problem calculus. Looks like a different problem, doesn't it? But actually, these 2 problems are intimately related. That doesn't seem obvious, does it? The area of the curve will be related to slope of the tangent. But it is, and we're going to see that in this course. But let's focus on the first problem. In the first problem, you've already sort of seen the solution of this. Define slope tangent line to this function like x at a f a. We need the derivative. Anybody remember how we did it? Yeah, something like that. That's something, right? And another way to do it was, some of you may have seen this. How many of you have seen that? And so the whole idea, the second one is quite easier for me to illustrate here. the whole idea is this. The idea is we just number say x x here, where x and a will reasonably close together. And we look at the slope of the secant line, which goes through these 2 points, right? And so, if I remember right, measure the slope of a line, it's rise over run, right? So it's f of x minus f of a. There's my rise, and my run is x minus a. Now, does this look like it's exactly the slope of the tangent line at black point? No. Do you think it's a little bit? Do you think that this is this fraction here? Is it too big or too little? In this. Looks to me like the slope of the tangent line might be like that. So it looks like the blue line's a little bit too what? Little? How would I get it exact? Well, actually, the idea behind getting it exact is something that it took us as a collective species of human beings thousands of years to come up with. And it's a simple idea, but at the same time, it's quite deep. It's part of what you're talking about here. You just let x get closer and closer and closer to a, and this approximation should get more and more and more what the black line is, and you do this thing called the limit. And actually, the limit was created way back when people started thinking about calculus, but it actually took over a century for them to really make this precise and kind of playing around with it. And that's what physicists do without really knowing what they're doing, but it worked out. And this is the so-called derivative. Remember this? Okay. So the derivative is something that measures slope of a tangent line, if you want to think about it that way, the instantaneous rate of change in function. And then what we started to do is we realized that derivatives are important. And so started looking at derivatives. Of basic. Okay. You might remember what the derivative of x is. Absolutely. Okay, so we do this, and then as h goes to 0, f x plus h, f x over h. Which is that. And look at me. Well, what was this? What about something more? Exotic? What if we want something like x squared or x to the fifth? Yeah. And actually, so here's a way you see this. This is x plus h, the n power, minus x to the n of h, right? Now, I'm going to be mathematically very sloppy here. What happens when you take the n power of this? This is yet, right? I mean, nobody wants to do this, but 8675309 power, right? But I don't know much, but I do know this. The first term that comes barking out of this is x to the n power. Do I agree with that? Does anybody know what the next term is? It's something like that. It's actually n x to the n minus 1 times h. Right? Because what you're doing is you're multiplying this together n times. Well, you can take n minus 1 x's and then 1h, and there's n ways to do that. But you see this pattern, right? For x squared, this would be 2xh. For x cubed, this would be 3x squared h. So I don't want to do this. I can really, but I'm going to do a shortcut. Every term beyond this one has at least an h squared, right? And junk is just the rest of the stuff. Everything has h squared, and there's an h cubed. So I pull an h squared and it's the same. I agree with that. Okay. Now you see any way to simplify that numeral? Okay, these are gone. And once those are gone, you see a common factor, h. So this is, let me cancel an h. Let's see, I kill that and kill this, so I get nx n minus 1 plus h joint. Now, what are you supposed to have is h goes to 0. And they're on. But notice, now I've got a formula work for implicit n, but it only works for positive n, right? I can't really do this if n is like -1 because it doesn't factor out like that, or -2, right? I've got a problem, right? Along basic functions, suppose I have this. Anybody remember the sign of that? Very good. And you do it the same way you did this, and you use the sign of the x plus h identity. And you've got to know some stuff about money, but is everybody comfortable with it? And how about this? Good. Everybody cool? Okay, so here's where we're at right now in the building of our empire of derivatives. I can do any positive power of x. I can do sine and cosine. But it seems like there's a lot of stuff. I'd like to be able to do negative powers of x. I'd like to do something like more sophisticated than x to the n. I'd like to be able to do all true functions. You might think of some rules that we have for derivatives that help us increase our menagerie of functions. Yeah. Okay, there's that. What else? Chain rule, right, I mean, now you're getting into some nuclear weapons right there, I mean, that chain rule is very, very powerful. Here's some basic. Suppose f of x and g of x are differentiable. So lawyers make it like this. All this means is I can just take the derivative. That's it. Then what's the derivative of f of x plus g? Like this one's the easier thing. Just do that. Just take it this time. To if C, then derivative. This one. Right, so you can just pull out a C, right? See it. Okay. Here's another one. Okay, this one's a little bit strange. But I remember how this one is. Everybody gets their turn given their derivative. Everybody's gets their turn. I wait, just forget it before we move on. What if I did this? F of x, g of x, a of x, b of x. It's the same the concept is exactly the same. It's just there's more players here to take turns. So we'll just take turns in order. Now it's G's turn. Now it's A's turn. And now it's B's. Product rule works real nice. And there's one more thing. You might remember how the quotient rule works. Probably. Let's see, this g of x squared. Right. Bottom times the derivative. We've all got our little things. Yeah, bottom times the derivative of top. Minus top times the derivative of bottom. Now, with this in mind, we've now conquered a lot more stuff. So for example, now there's a trig function we haven't had, right? Does anybody know the derivative? That's exactly right. Secant squared x. But you know what? Sometimes it's easy to get something like that. So what happens if you're in a pickle? You can't remember. Well, this is actually And now you can throw the quotient rule out. So let's check. Okay, let's do this. It's bottom square that we want bottom. Right. Bottom times the derivative of top. I'll put the thing that's the derivative of square. The derivative of sine cosine minus the top times the derivative of bottom. What's the derivative of bottom? Good, good. So this is which looks like that on a hot plate until I make one observation. You like see how this thing? Like that sucker on top is just and now you can do voluntary functions. Those arbitrary functions are quotients of sine. Right. So there you go. And negative for say secant x, tangent x. And this allows me to put together more exotic. Well, in fact, because how many of you see this notation? Oh, this means take the derivative. Now remember, a moment ago, we couldn't do negative powers of x, right? But now the quotient rule totally saves our butts in the following sense. What's another way to write x minus n? Good, good, good. Absolutely. 1 over x(n). And now that's a quotient of two things that I know what the derivative is, right? So in theory, I can work this out. Quotient. Now square that. X to the 2n. Right? Now let's go through the math. Bottom times the derivative of the top, which is c. Right? Minus top times the derivative of the bottom, which is n(x)(n) minus 1. That works here because n is, I know the derivative of that. So this becomes just 2n. So let me simplify this further. So basically what I'm doing is I'm sort of canceling out this power here. So I'm going to subtract n minus 1 here. I'm going to subtract n minus 1 and the exponent down there. Which is so let me summarize. Notice this formula is the same, right? As for positive power. You just drop the exponent and subtract it. So in summary, this is what one of the things the quotient rule's got us. Well, it's got us all the trig functions. It's also got this. Okay, any questions? So here's one for y'all to do here. Okay, somebody tell me what the derivative is. What's taking the longest amount of time on the problem? This quotient rule? That is that what eating at the time? Okay, so let's do this. What's the derivative of this? Cosine, derivative of that. Derivative of this pain, right? Maybe not so bad. The only difference between calculus and algebra is this notion of a limited number. That's it. Everything is algebra. Algebra used to be your enemy, now it's your friend. Use it to make your life easier. Swim at apple. This is 2x cubed over x. This is 3x. And if you like, you can find this. I don't care so much. So f prime of x is cosine x is 6x minus 4x minus. Don't be afraid to use a little bit of algebra to make your life easier. Okay. How about this? Oh, not bad. I'm gonna take this. Order this flow. How about this? What is the major rule that you apply to this? Well, yeah, but let's assume we're quotient. This is first and foremost, this is product. You got two things going on. You got x squared, you got sine 2x. The faith you brought up an important point. Because x squared, I can take a derivative. Sine 2x is a little bit more problematic. Like anybody gets out of this. Oh, you have to wait and rewrite sine 2x. There's some trig identity in there, right? This is actually 2 sine x. Okay. Let me rephrase the question. How many of you have ever seen this? You know, sometime maybe you had therapy afterward, but you saw it sometime. This trig identity, sine 2x is 2 sine x. In my class, I will give you these identities for free. It's your responsibility to know that they're out there somewhere and maybe I want to use them. But if you ask for them, I give them to you for free. Okay? So I could rewrite this, right? So now I've got and that's a product of 3 things I will check and make through it. Right there. So derivative. So I'm going to give you the piece. Okay, so 2x squared 2 start. Now whose turn is it? Sine x. And what's the derivative of sine? So it should be 2x squared cosine x. Cosine x. Do I agree with that? And now whose turn is it to have a derivative? And what the derivative of cosine is? By the way, in fact, here's a good sort of rule of thumb in my class. Only simplify something if there's something in it for you, right? If you need to find a root of an equation and simplifying makes it easier, don't gratuitously simplify. This step demonstrates the calculus, and that's all I'm doing. Now, of course, if this had been sine 1/2 x, I would have been totally rosy, right? I just happen to know, or even see by knowing identity sine 5x. They're out there, but I mean, I would seriously. I don't know. There's another way to handle this problem, and that brings us to what was brought up earlier by both y'all, and that is the change. f of x and g of x are differentiable. Again, this only means that I can take the derivative of it. Then, if I want to take the derivative of f of g of x, anybody remember what that is? Right. Work your way inside of the derivative. It's f prime of blob times the derivative of the blob. F prime, whatever derivative. Now, of course, you can change these up more complicated. You can make these things arbitrarily. I'm going to work this. The first application of the chain rule is let's do this again. And now we don't need this tree. Now, first and foremost, this is a product rule, right? So let's go through it. I'll go through more steps than I need here. Okay, first x squared is your term. And your derivative is 2x times sine 2x. Agree? And now it's your turn to be left alone. And we take the derivative of sine of 2x. Well, now, what's the derivative of sine of 2x? Cosine of blob times the derivative of blob, which in this case is. So this is 2x sine 2x plus 2x squared cosine. Notice I have two terms, whereas in the previous way I worked this, I had three terms. If you compare those, they will look different. There are trig identities to show you these two are actually the same. Interesting. The chain rule also means never have to use the quotient. Right now, let me be practical for you all. I always remember the quotient rule because in a lot of situations, it's easier to do and it's easier to manipulate, especially if you want to find places where the derivative is 0 or whatever. But in theory, you never have to do it, or you can rewrite it. All you really need to know is because this is derivative f of x times g of x minus 1 power. So let's see what happens. First, I'll take your derivative. And now I'm going to take the derivative of this guy. Now, what do I have? I have log to the negative 1 power, right? How do I take the derivative of log to the minus 1 power? It is minus log to the what power? Negative 2. And am I done? No, I've got to work my way inside that parenthesis. Times the derivative of what I find inside derivative of log is 2.x. Everybody okay? Right. So this is f prime of x over g of x minus f of x prime of x over g of x. Right? Because this is f of x over g of x. Agree? And this is negative f of x times g prime of x over g of x squared. Now, just bring a common denominator. Another g of x here, another g of x here. And I get my familiar portion. Let me give you something. You know, any real number. I'm going to give you this. I'm just going to use it. I'm going to justify this later. So this is the general power rule. So far, we have shown that this works for, we knew it was true for positive integers. Now we've shown it's true for negative integers. Now, I'm saying this is true for any real number where this is in the middle, right? So for example, if n is for some values of n, x has to be positive. Right. So for example, if n is 1/2, x is 1/2, that's the square root. You can't have x, right? But as long as this function is defined in the square root, you can use that. Let's do another one. I'm going to do some more complicated chain rules, and then I'm going to have a problem sort of segue into the. Okay, so how are we going to do that? Does anybody see, besides you, I know you got it. Does anybody see something that we can do notation? Very good. The square root is, it's all sexy and stuff. The fact of the matter is, it's not really good for doing chain rules, right? It's kind of easy. This is right, a big fat block, 1/2 pound. Y'all figure this one out? Okay. Let's go. First, I have block with 1/2 power. What's the derivative of something 1/2 power? What power? Right, 1/2 minus 1, so. Everybody okay with that? Now, chain rule says, hey, Jim, you ain't done. Now you gotta multiply that by the derivative of what you find inside. And what's the derivative of the times? And again, you know what, you're doing calculus, don't bust. How about something like this? Let's try this one. Oh, right? Yeah, that's a small. Anybody even finished your stuff? Yes. Oh, okay. Okay. So. So let's go. So I'm going to kind of color this. So most thing, none of this stuff is very hard and common sense. I mean, it's hard, but it's not hard. The not hard part about it, taking derivatives, it's fairly simple. Powers and signs, those things. The hard part about it is you've got to be a good accountant, right? And just kind of figure that out. So the first thing I come to, sine of block. Agree? What's the derivative of sine of block? Cosine of whatever block. So this is just a copy job here. And in fact, let me write this way. Sign, so I did the same thing before. This is cosine, 2 cosine x half. There you go. That's the first change. Everybody agree? But now, I've got to multiply by the derivative of what I see inside. And you know, when you're first getting warmed up to this, you could write this times the derivative of this. Everybody agree with it? By the way, this answer is right. It's just incomplete. Right? Because it still needs to evaluate this. Everybody? So let's keep going. Let's try to evaluate it. Okay, so now what's the derivative of this? Now it's got a little simpler. What's the derivative of cosine? Negative sine. Wow. But am I done taking the derivative of this? Right? Derivative of this is 2 minus 2 sine blah times the derivative of blah. Again, this is right. I'm going to try to finish this off in one step. Now, what's the derivative of this? It is 1/2 x cubed plus x. Negative 1/2 power. And there we go. Let me do this. It's kind of this the hardest. Actually, I'm gonna have this one is. This one was created in the fires of Mount Doom by Sauron's that because this one is pretty evil. Right? What do you suppose the first thing I should do before I can start bounding off into the derivative land? That's right. Let's clean this up a little bit. Let's help ourselves out. f of x is, let's think about what this is. This is cosine x to the fifth plus x to the half. I mean, this is what I would do if I was punching in the calculator. First, I take x to the fifth plus x to 1/2. I take the cosine of that. Then I take the fourth root of that. Oops, and right. Take the fourth root of that. And then I would add tangent x to it. And I would take the third root of that. And then I would add sine x to it. And I would take the square root of that. So that's my custom rewrite. This may take it. Right, this is awesome. But you know what? We'll persevere. And again, take confidence in the following fact. There's nothing in here that is hard. Nothing's hard to take a derivative of. It's just fractional powers, tangents, sines, cosines, etc. So hard as being good. What's the first thing that comes? What's the first outside? That's right. This is all a big fat block. Right. So I'm going to key on that. 1/2 blob. Third. To what power? -1/2. And there we go. But the chain rule says, hey, Jim, you're not doing it. I've got to take the derivative of what's inside. And what's inside is an easy piece plus another mess, right? Because it's sine x plus that crazy thing. Everybody agree with that? So, what is the derivative here? The derivative of sine is cosine. That was the easy part. And now I've got to take the derivative of this mess. Right. What's the first thing I come to in this mess here? Right, it's blob to the 1/3. So I should get 1/3. Everybody agree? Catch your breath there. Everybody with us. 1/2 blob to the -1/2. Then I had to multiply by the derivative of this. Derivative of that is cosine. That was easy. Derivative of this is 1/3 blob to -2/3. But I'm not done taking the derivative of this. I've got to multiply. I'm not done taking the derivative of this. I've got to multiply by the derivative that's inside. And what's inside is this. So what's inside is tangent x plus some other mess. Anybody remember what the derivative of tangent x is? But the other bit, the other part of the mass is 1/4 something to the 1/4 power. derivative of this is tangent x, derivative of this is 1/4 log to the minus 3/4. See, now I'm not taking the derivative of this. I've got to take the derivative of what's inside, which is just this bit. So I have cosine of something. What is the derivative of cosine? So you're multiplying this bit by negative sine of x bit, so it's 1/2 times the derivative of what's inside there. This last bit is 5 x 4, it's 1/2 x minus. Close this parenthesis. Close the red parenthesis. And I think these are among the hardest chain rule problems. So again, there's nothing difficult to see. It's all the derivatives are fairly easy. It's just hard to sort of keep track of where you're going. And I like your method of taking apart the blocks easier, piece by piece. One thing that you could do until you're warmed up, now most chain rules are easier, but you can go 1/2 block and minus 1/2 and like derivative of what's inside, and do another step and another step. Are there any questions? Does everybody see how this worked out? Okay, questions? All right, so I'm going to segue a little bit before we're going to focus on a little bit more tomorrow. I'm going to start with a practical. Anybody describe what this looks like? Well, so R is just some number. So in fact, I'm going to look at the specific answer. But can you describe what all these points look like? Think back to the days when lab was expensive. It's what? No, it's not linear because you got the powers that are not one. Let your thinking come full circle. See, it is a circle of radius r. So, for example, let me do specific. Yes. This is one of my favorite circles. It is centered at the origin and it's got radius 5. So, minus 5. Now, here's the problem. 5 slope 10 circle going. Notice that 3 minus 4 is on this circle because 3 squared is 9, 4 squared is 16, adding 5 is going on here. And I guess that would be called I'd be about right there. By the way, can anybody tell me what the anything about the slope at all? Slope of the Something very minor. Very good. I expect to get a positive answer. My goodness, how do I do this? Here's one of your big problems. What is the tool that you use to find slopes and tangents? Well, so when I think, oh, okay, so you get these problems to do in 240, whatever, find the tangent line to the function point, find the slope of the tangent line. What jumps to your mind? I'm going to have to use the. You're going to have to use the derivative, right? And your derivative is defined for a function. This is not a function. Somebody tell me why this is. You mean vertical line, but it's right. Notice the y-axis, for example, hits this sucker more than the point. This isn't even a function. And of course, I want that function. So if I were to try to solve this, here's the thing about this. If I solve for y, I get that, right? And so this would be what I have to take the derivative of, right? Or is it? Does everybody see how I got this? Okay, so let me take one more step here. I can certainly do that. And then I just took the square root of the whole shebang, right? But that doesn't work. It's like 21. Let them talk to me, speaking to those voices. And here they go and say, look at this thing right here. Why is the square root of 25 minus x squared? It's telling me in this solution that my y coordinate is always positive. Right? But remember, the square root of anything is positive. Look at this point. Is the y coordinate positive? No, it's not. Take the square root, I have a plus or minus solution. So part of the circle is actually this piece right here. The negative. Okay, so that was my first right. Is if I'm not careful, it's a solution. Well, let's just persevere ahead. Okay, now I've got to take the chain, which is another 85. Okay, so I have the log of 1/2, so it's minus 1/2 log to the what power? Times the derivative of what's inside, which is and I will clean this up some. Those minuses cancel, I can next on top of the square. Now, what do I plug into this? Get my answer. Right, I need to plug in this point here, which is relevant, the x coordinate and y. Yeah, it's because this is y prime in terms of what you grab an x, x is the important thing. So y prime 3 is 3 over the square root 25 minus 9, which is 3 quarters, because that's 16. And your observation is true, it's positive. Right? So this seems reasonable, right? Does anybody know? There's actually another thing. Anybody know anything about the geometry of the circle? If you draw a radius to this point, the tangent line is perpendicular. You'll know that. Yeah. And this slope right here is actually rise over run. So the slope here is minus 4/3, and the negative reciprocal that's so this answer actually exceeds. But I had to go through a bit of pain here. And if I really wanted to ruin your day, all I have to do is change this to some other function where it's part of the extract the root. So for example, let me do this problem another way. So let's remember the answer that we got. So the answer is 3/4. Now, here's the idea. This is called implicit differentiation. By the way, implicit, that's an English word. What does that mean to you? If something is implicit, what sort of a companion word means sort of the opposite? How about explicit? You ever heard that? Explicit is it's out there, it's very, the explicit is something that's just absolutely clear, stated clearly. Implicit means it's subtle. I might not directly say this, but implicitly I expect you to be able to do all the stuff you do, even though I might not explicitly have said that. Right? So what we're going to do is we're going to look at this function. This is our friendly neighborhood circle. And we're going to assume y is some function of x. And actually, we went through the pains of finding this function over here explicitly because we could. We took a square root and we said, oh, it can't be the positive square root, it's got to be the negative. We went through some pains to do this. There are many situations where you're not going to be able to find this function explicitly. We'll assume that that function is there. It's going to be nice, which is amazing. So here's what this function becomes, and I'm going to do this in parallel. So if y is equal to f of x, let's just write this equation this way. Right. Just replace y with f of x. Right? And I'm going to kind of do this in parallel. I'm really doing the same thing. I just want to get y'all used to some notation. Now, what I'm going to do is I'm going to ddx this thing. Means I'm going to take the derivative of this equation here with respect to a. Now, somebody tell me, pray tell, what is the derivative of x squared? 2x. No worries. What is the derivative of this thing? This is more complicated than just x squared, right? So I've got an f. So what do I got to do? I got to do the chain rule. That's exactly right. So if I ddx this thing, this is going to be 2 blob to the 1 power. Right? But I'm not done yet. What do I got to multiply that by? Derivative of what's inside. And now what happens when I take the derivative of the other side? See, the derivative 25%. And now this allows me to search for my f prime of x. So I get 2 f of x, f prime of x is minus 2x. By the way, I can cancel the 2's from f prime of x minus 2x over f of x. Okay. Any questions? I'm gonna do this in parallel over here. And let me for instance, put that y. What is the derivative of 2x, or I'm sorry, x squared with respect to x? Same thing. What do I have to do here? Well, y is not x, y is the same function, so this is a chain. This is 2y, 1 times the derivative of y, which is y prime for dy dx. And what do I get here? And I'm cancel twos, make y prime. Now notice when I plug in the point of the circle, x is -3, equal to -4. So notice this is the same thing here. I get minus x. I cancel my twos and like that. Notice that this is minus x over y. Again, you get the same answer. So do a quick example, and then we'll take our quiz for the day. And I'll take up your quiz 0 too, where you told me a little bit about yourself. Fine. Tangent. 2. Curve. Defined by, let's say, x squared plus xy plus I cubed is equal to 7. I'm sorry, it's 3. Add 1. By the way, anybody know what this curve looks like? Yeah, I got no idea. Can figure it out. It'll take quite a while. But remember how we solved for y when we did the circle? Good luck, right? Does anybody know the cubic formula? It actually exists, but it is death on a hot plate, right? I mean, it was seriously. It would be longer than this chain rule right now, right? Just to write it down. Nobody wants to be taking the derivative of this. And not only that, all I got to do is change that 3 to a 5, and you cannot play it. Nonetheless, I can find the tangent line, whatever this curve looks like at that point, without knowing explicitly. Yes. Let me point out first that when I plug in 1 for x and 1 for y, I get 1 plus 1 plus 1. So this point is on this curve. Now, let's ddx the crap out of this. What's the derivative of x squared? I'm liking that. What is the derivative of x times y? Well, this is a product rule, isn't it? So let's take their terms, get their derivatives taken. What's the derivative of x? Times y. Now it's y's turn to have its derivative taken. What's the derivative of y? With respect to x, it's y prime. Everybody okay? What's the derivative of this thing? 3y squared. And am I done? Gotta multiply that by the derivative of y, which is y. And what's the derivative of 3? By the way, or how many of you are a little bit confused? Where the heck that y prime is? Does that bother you a little bit? Okay, so let me straighten that out. You actually do this all the time. You just don't realize it. Let's take the derivative of this. Respect to x. Let's do the chain rule. Let's be super explicit about it. Derivative of x is 2x to the first times dx dx. Derivative of x is respect to x. That's the derivative. What's the derivative of this? It is 2y to the 1 dy dx. No reason why that should be 1. So you can just write this down. This is 2x plus 2y y prime. Does that make sense why that y prime is there? Because the x prime is there too. It's just okay, everybody with me on this? Okay, so what do? I need to find y prime to find this tangent line. Everybody agree with that? So I could solve for y prime, but please don't. Just go ahead and plug in. Here's the equation I have: 2x plus y plus x y prime plus 3y squared y prime equal to 0. Now plug in x and y equal 1 and see what happens. And 2 plus 1 plus y prime plus 3y prime 0. And this allows me to solve the 1. 4 y prime is -3. This must be a 3/4 of that. It's coincidence. Y prime is -3/4. And so the tangent line, just to be complete in its problem, I get y minus 1 minus 3/4 x minus 1. So that's in point slope. That's good enough. Okay, any questions on this? Any questions? Okay, we got about 20 minutes left. I am going to give you your first quiz, which in theory should be kind of all review. Not super easy, I don't think, but well, some of them. But yeah, make sure that you can do this. I'll post the quiz. And by the way, thank you for noticing that thing. I'll try to compare it. I'll put it in the module to see that will be updated. I do your best on this, and then y'all have your can I take your stuff here? Oh, yes. Oh, yeah, for the first day. In general, I don't want you to, but yeah, you can look at it.